Sasha Feldmann has put out another paper. You might know that we're huge enthusiasts of Sasha. He's done some excellent work, one of which we referenced throughout, which is Feldmann's 23 Advanced Materials Papers, Fundamentals, Advances, and Artifacts in Circularly Polarized Luminescent Spectroscopy. And we used his template as a means of optimizing our CPL instruments even beyond their already excellent potential. But this one is a review paper, Chiral Light Matter Interactions in Solution Processable Semiconductors. It just came out in April of 25. And if you would be interested, here's a quick read through on the introduction. The concept of chirality was defined by Lord Kelvin already in 1893 by stating that any geometrical figure or group of points could be called chiral if its image is in a plane mirror, ideally realized, cannot be brought to coincide with itself. In molecules, chirality manifests as pairs of enantiomers, which are mirror images of each other. Chirality plays a crucial role in functional materials across fields. It is pervasive in nature, with many important biomolecules such as sugars and much of the proteinogenic amino acids being homochiral. Familiar examples for synthetic materials for which chirality must be accounted are found in drug design, in which different enantiomers may produce different responses in the body. Chiral functional materials have also seen a surge of research instruments for their interests, for their potential application in emerging quantum, photonic, optoelectronic, and spintronic technologies. The crux of utility in these applications lies in their interaction with light. This interaction depends in particular on the polarization of light, that is, the oscillations of the electronic and magnetic field vectors of a light wave. Light itself is also chiral when it is circularly polarized. In this case, the electronic and magnetic field vectors rotate around the direction of propagation. Microscopically, such circular polarization is the manifestation of a photon's spin angular momentum, which, due to its photon's bosonic nature, has values of either plus h or minus h corresponding to the right-handed and left-handed circularly polarized light, respectively. It should be noted here the handedness of circular polarization is based on the perspective of the receiver, although the opposite convention from the source can also be used. If desired, chiral light can interact with chiral molecules and nanostructures as they absorb and emit linearly left circularly polarized or right circularly polarized light, preferentially relative to the underhandedness, resulting in circular dichroism, which we're all familiar with, and circularly polarized luminescence, respectively. Obviously, CPL is a much less commonly used technique so far. And then I'm just going to jump to the final couple of paragraphs. With these exciting developments at hand, methods to detect chiral light directly are highly sought after. Chiral photodetectors could ease miniaturization efforts and thus allow leveraging the full potential of chiral light in large-scale applications. However, current applications still fail to combine a high selectivity for circularly polarized light with high sensitivity, high response speed, and long operational lifetime. In the future, we expect that chiral open shell systems and chiral dilute magnetic semiconductors will provide new avenues across fields, such as in the exploration of the interplay between chiral light and spin and the development of efficient CPL from doublet states for CPLEDs or in emerging spintronic and quantum technologies. The exploration of chirality-related phenomenon currently fuels innovation across disciplines. Hence, it is time to acknowledge the full potential of chiral light-matter interactions in new mechanisms and real-world applications alike. This potential can be harnessed through material chemistry, in which organic, inorganic, and hybrid semiconductors can be made chiral while still maintaining their superior electronic properties. Such chiral semiconductors open ways to control and emit chiral light as well as to manipulate spin, with the underlying mechanisms still remaining unclear, as the respective techniques to study such phenomenon will also need to be developed. Such chiral light matter interactions will enable dramatic efficiency boosts to existing technologies like LED displays, while also allowing for the development of entirely new applications for example, in quantum information processing. And there's tons of other stuff in this wonderful Nature Reviews Chemistry paper, Volume 9, April 2025, that you might enjoy reading. So again, another superb paper by the Feldmann group. If you're interested in CPL or CD, give us a call.